All right, this is a continuation of section 1.5 in your intermediate algebra book. We're going to pick up with example 12, which is at the bottom of page 48. And I'm trying this new thing with the screenshots, so we'll see if this works. All right. Ellen works in the Learning Center. Her salary can be modeled by the function s of x equals 7.5x, where s is the salary in dollars and x is the number of hours spent working in the center on a given day. So this is the function we're going to work with. S of x stands for salary. X stands for how many hours she spent working. So 7.5 is her hourly rate of pay. Letter A says, what is her salary if she works for 5 hours? So we're going to start by writing the function. I'm going to scroll this up a little bit. I can write down here, S of x equals 7.5x. We're working on part A. What's her salary if she works for 5 hours? So let's mark this as part A. If she's working for 5 hours, x represents the number of hours, so we'll substitute a 5 in there, and then after we simplify this, we'll have the number of the amount of her salary. So her salary will equal 7.5 times 5, which comes out to be 37.5. So her salary, and we're going to, of course, write these in a complete sentence. Her salary for 5 hours is, don't forget the dollar sign, 37, and 0.5 is not appropriate because this is dollars and cents, so you do need to express it as dollars and cents, so $37.50 would be appropriate. All right, part B I don't have in the screenshot, but we can look at it here. Part B says, oh, I do have it. I'm sorry. Let's scroll up and see what it says. If her paycheck is $150 at the end of the week, how many hours did she work? And again, using this same function, they're telling us her paycheck or her salary. So we're going to substitute s of x with 150 here, and then we'll be solving for x or how many hours she worked. So let's scroll down here and write this as s of x equals 7.5x. We know that her salary for that week was 150, and we need to find out how many hours she worked. So to isolate this x, we will divide both sides by this 7.5. And of course, you're going to want to get your calculator out to do this. That's fine. 150 divided by 7.5 comes out to be 20. So again, in a complete sentence, she worked 20 hours for $150. Okay, example 13 is on page 49. This is actual screenshot from your book. I'm going to zoom it out just a little bit. All right, so it says, Dexter recently graduated from Valencia College and has a student loan of $5,000. He paid $1,500 with his tax refund. He agreed to make a payment of $250 every month in order to pay off the balance. His payment function is given by p of x equals 250x plus 1,500, where p of x is the payment in dollars and x is the number of month. Okay, this says p of x is the payment in dollars. I really think it really means p of x is the amount of money he owes. So 250 times how many months he's paying plus the original 1,500 he put down at the beginning. So letter A says, how much of the loan will he pay off after 7 months? So let's rewrite, see if I can go up a little bit and maybe zoom. I can write over here, I think. let's rewrite the function. P of x equals 700, no, is it 750? I don't think so. It's 250. I just cannot write today. That's fine. 250x plus 1500. And that's the function. Letter A asked us, how much of the loan will he pay off after 7 months? Well, since x represents the number of months, we'll replace this with 7. And that will say P of x, or how much he's paid, 250 times 7 plus 1500. This is an interesting fluorescent effect here. So 250 times 7 is 1750. So that'd be 1750 plus 1500. So this will equal 1750 plus 1500 is 3250. So after 7 months, he has paid $3,250. All right, let's go over to part B. Says, how long will it take him to pay off the entire loan of $5,000? So if we're looking at this function, the entire loan of $5,000 would be your P of x, or he will have paid off $5,000, and then we're going to have to solve to find out how long or how many months it will take. So let's scroll up down here and let's write this here. Starting with the function, P of x equals 250x plus 1500. This is part B. To pay off the entire loan means he will have paid off $5,000. So we're going to replace that P of x with the 5,000, the entire loan. All right, so this is how much he wants to pay off, the entire thing, 250 times how many months plus the $1,500 down payment. And we need to solve for x here. So to isolate this x, first subtract the 1,500. Or some people learned it as moving it to the other side. That gives you 3,500 here. And then divide by the 250. Again, you can use this. You can use your calculator if you like, whatever it takes. You'll end up with 14 here. In a complete sentence, it will take 14 months to pay, whoops, off the loan. Okay, on page 50, we're going to talk about domain a little bit more. Starting with example 14, we're being asked to find the domain of this function. S of x equals x squared plus 4x minus 5. And on that, at the top of that page, you can find the definition of any polynomial function. And what constitutes a polynomial is that it has a couple terms, variables, constants, and non-negative or positive exponents that are not fractions. And this right here is what constitutes a polynomial function. If you've never seen one before, there are no fractions, there are no negative exponents. The domain of any polynomial function is all real numbers. Okay, in interval notation, that's negative infinity to positive infinity. On example 14 on page 50, you can actually see that the graph of this polynomial function looks something like this. It's what we call a parabola, which we're going to study a little bit more in Chapter 6. But if you're talking about domain, you're talking about all the x values, and you can see this goes to negative infinity all the way to positive infinity. Now, not all polynomial functions look like this, but they all have x values that go from negative infinity to positive infinity. Example 15. Which is on page 51, is a different kind of function. It's a rational function. A rational function is simply a function that looks like an algebraic fraction. Rational is just a fancy word for fraction. And you can see this does. It has a fraction bar with a numerator and denominator, and both the numerator and the denominator have variables in it. This is a rational function with a polynomial in the numerator, a polynomial in the denominator. The domain of a rational function is all about this denominator, because with fractions the denominator cannot equal 0. So to find the domain, you just take the denominator. You can ignore the numerator, and you say this denominator cannot equal 0, because if that denominator equaled 0, the fraction, the entire function, would be undefined. So we're going to do that. We're going to take the denominator, which is the bottom, x plus 2, and we're going to say x plus 2 cannot equal 0. And that not equal sign, it behaves just like an equal sign. To isolate x, then, we have to subtract this 2. So we're going to subtract 2, and we get the statement that x cannot equal negative 2. The reason for that is, if you look back at the function here, if I substitute a negative 2 in here, negative 2 plus 2, it would make the denominator equal 0. So x cannot equal anything that makes this denominator equal 0. So to express this in set builder notation, we just say x such that x cannot equal negative 2. That's set builder notation. Interval notation is a little bit more tricky, because if you imagine that this is a negative 2 right here, x can be anything except negative 2. So everything else on that number line would be shaded, and there'd be an open circle at negative 2 here. To write this in interval notation, you actually have to write an interval for this piece and an interval for this piece, because they do not touch in the middle. So that's going to look something like negative infinity to negative 2 with open, union with negative 2 to infinity. So this interval right here describes this piece of shading. This interval describes this piece of shading. They do not touch in the middle, but they are both part of the same set, so that there is a union there. Example 16 is the same type of question. It's on page 52. F of x equals x minus 5 over x minus 3. And again, this is another rational function, so it's all about that denominator. The denominator cannot equal 0, so we'll start with that statement. X minus 3 cannot equal 0. When you add 3 to both sides, you get x cannot equal 3. So to write this in set builder notation, x such that x cannot equal 3. In interval notation, again, just like we showed before, that this means there would be a hole at 3. So you're going to have to write two different intervals. Negative infinity to 3, union with 3 to infinity. And in case you're wondering, why are we now using parentheses? It's because this is open at 3. It doesn't actually ever touch the 3. So we only use brackets when numbers are closed. We use parentheses when they're open. All right, example 17. another rational function to find the domain. It's on the top of page 53. It says s of x equals 2x minus 7 over 3x plus 4. It's all about the denominator cannot equal 0. So you start with that statement. 3x plus 4 cannot equal 0. Solving for that, we first subtract the 4. 3x cannot equal negative 4, and then divide by 3, and we get x cannot equal negative 4 over 3. In set builder notation, x such that x cannot equal negative 4 over 3. In interval notation, it will be not braces. It will be parentheses, negative infinity to negative 4 over 3, union with 4 over 3 to positive infinity. All right, for example 18, on page 54, we're going to a different kind of function. D of x equals the square root of x plus 7. This is called a radical function because this square root symbol is a radical symbol. So this domain is different from a rational function. In a radical function, the radicand, or this expression here under the symbol, has to be greater than or equal to 0. It has to be a positive number. So let's write that as a rule here. The radicand, that's the part under the symbol, if you want to write that under the square root symbol, has to be greater than or equal to 0. So we're going to take that radicand, x plus 7, and we're going to make it say this is greater than or equal to 0. It has to be a positive number. We're going to talk about this again more in chapter 5, but a negative number under this radical symbol makes this an imaginary number. It's not a real number, therefore cannot be on the number line or on a graph. So this has to be a positive number greater than or equal to 0. And again, this greater than or equal to works just like an equal symbol unless you multiply or divide by a negative number. If you multiply or divide by a negative in the process of solving here, you have to flip the direction of this symbol. The only thing we need to do to solve for x here is subtract the 7. So that's what we're going to do. And we have x is greater than or equal to negative 7. All right. In set builder notation, that's what it looks like. X such that x is greater than or equal to negative 7. Now, in interval notation, again, we're going to just draw a little example here. If this is negative 7, x is equal to it, so it's closed, but this is saying x is greater than, so everything greater than the negative 7 is shaded. So all of this is your solution. So in interval notation, brackets, negative 7, comma, infinity, and of course infinity always gets parentheses. Example 19 is the same type of function, a radical function. H of x equals the square root of 6 minus x. To find the domain, it's about the radicand has to be positive or greater than or equal to 0. So we're going to take that radicand, 6 minus x, make it greater than or equal to 0. And then we're going to isolate x. First thing we do, subtract this 6. That negative sign in front of that x, though, stays with it. So negative x greater than or equal to negative 6. But you're not done because you don't want this negative sign here. To get rid of it, you divide or multiply, whichever way you learned it, by negative 1. But this is what I was talking about in the last example. When you're working with these greater than, less than symbols, if you multiply or divide by a negative, this has to flip. So this symbol will now be less than or equal to. That doesn't change what happens with the numbers. This becomes a positive 1x, and this becomes a positive 6. So x is less than or equal to 6. In set builder notation, x such that x is less than or equal to 6. In interval notation, if this is 6, x is equal to 6, it's now shaded this way, less than. So negative infinity to positive 6, brackets on the positive 6 because it's closed. All right, if you're following along in your textbook, we're up to page 55. About in the middle of page 55, there's a section called graphing functions. You can see there's a t-chart that you get giving values for x and y, and then there's a graph of a parabola over here. I'm actually not going to go through this because we have an entire chapter about graphing functions. So if you're looking for some more detail about graphing, especially graphing parabolas, you can look for the chapter 6 videos. All right, so this is a picture of page 55 if you're following along in your book, and you can see on page 55 and 56 there are examples of different types of functions and what their graphs look like. I right now do not have the ability to record the graphing calculator, so you can check one out. You need to learn the names of these functions. So in other words, this is a straight line, it's called a linear function. This is a parabola, it's called a quadratic function. This type of little curve here is a square root function. This sideways s thing is a cubed root function, and there are more on page 56. What you need to do is check out your graphing calculator, which should be a Texas Instruments 83 or 84, and you can use a plus if you want. Check them out from the library or the Math Depot, and go through these steps here to graph these on a graphing calculator. All right, and this is the second page of those functions. There are 7 total functions. This one is called a cubed root function. This is called a reciprocal function, and this v is called an absolute value function. Just take a few minutes to grab a graphing calculator. Make sure when you come to class you bring the graphing calculator with you, and we can review these together there.